On the website of drawdown.org, which ranks the top 100 solutions to global warming, large methane digesters are ranked number 30, and small methane digesters, such as I do my research on, are ranked number 64. They are thus considered very important. But systems thinking and an appreciation for synergistic multiplier effects suggests to me that simple technologies to shred and grind wastes, coupled with microbial transformation and the anaerobic process of digestion, centered on urban organic residuals as the primary feedstock, lie at the very heart of sustainability and should be ranked even closer to the top of our priority list. I will endeavor to show here today that size reduction of wastes through grinding, coupled with microbial transduction into value, processes which humanity by and large missed for the past 2 centuries or so as we nurtured and invested overwhelmingly in our infatuation with the combustion and chemical transformation of fossil hydrocarbons, is actually the keystone solution for a resilient and thriving future. And I will try to lay out the argument that once we have embraced the concept that our so-called waste materials should be routinely ground down into smaller particles, improving their surface area to volume characteristics, a highly beneficial symbiotic relationship with microbes becomes possible, starting with the mutually beneficial transduction of wet organic wastes into fuel and fertility and a host of potent biochemicals by the descendants of the first life forms, the prokaryotic archaea, and that these keystone solutions should be the logical core of our sustainability efforts. The organisms on the screen are just a few of our partners whose cooperation becomes possible once we've embraced the concepts of radically improving surface area through grinding and symbiosis. I will start by suggesting that biodigestion of municipal solid waste should be considered the solar plexus of the food, energy, water nexus, and that its derivatives and the processes this simple central solution then permits is what can get us from the downcycling cradle-to-grave nightmare we've fallen into and forward toward the true cradle-to-cradle industrial ecology made famous by McDonough and Braungart that can lead from the cowboy economy to what Nobel Prize-winning economist Kenneth Boulding called the spaceman economy. While there is no silver bullet technology to put our civilization on track toward practices that stay respectfully within our planetary boundaries and help us achieve all 17 of our Sustainable Development Goals, responsible anaerobic digestion of organic waste materials that are currently causing severe health and environmental problems deserves to be considered, I feel, the first investment we can make so that we can simplify all the other issues we must grapple with. There are both obvious and obscure reasons for this. Let me start with the most obvious first. We all know that having an abundant supply of cost-effective energy is the key to being able to keep civilization prospering, and that the major criticism of renewable energy technologies is their intermittency. It is said that the sun doesn't always shine, the wind doesn't always blow, and the rivers and streams don't always flow. The truth is that actually the sun does indeed always shine and is inexhaustible from the perspective of the anticipated length of our continued human presence on this planet, but the rotation of the Earth and the presence of cloud cover and shading make it seem that solar energy is inconsistent. The same is true of wind and water power, two derivatives of the sun's radiant energy, and even of biomass, the accumulation of solar energy in the chemical bonds of terrestrial plants and algae through photosynthesis. They don't always occur when and where and at the rate we want them to, or in the quantities we desire. Because of this, we talk about energy storage as being the big issue for renewable energy. We fret about how we can concentrate diffuse sources of solar power and how we can store it in the quantities we need. What has often been overlooked, until fairly recently, is the reality that our organic consumer and production residuals, often thought of as wastes, are a kind of solar storage battery, that they represent an abundant source of biomass that is readily convertible into energy. Beyond the obvious immediate use of the biomethane and fertilizer that results from direct anaerobic digestion, there are a wide variety of environmental solutions that this first stage processing make possible, and that, despite receiving less attention, actually hold an incredible amount of promise. In many ways, the story of how biodigestion can facilitate other environmental sustainability initiatives mirrors that of the development and deployment of LED lights. Incandescent light bulbs, according to Paul Hawken in his book Drawdown, the most comprehensive plan ever proposed to reverse global warming, are, quote, heaters that give off a little light, while LEDs are light bulbs that give off little heat, end quote. That crucial innovation, durable semiconductor bulbs that emit light with almost no heat loss, suddenly enabled people all over the world to power very bright lights using very little power. Hawkins states, quote, their low energy use makes it possible to turn on the lights with small solar cells, replacing expensive kerosene lamps and their noxious fumes and high greenhouse gas emissions. End quote, page 92. I personally lived this reality in Dar es Salaam, Tanzania, staying with a family that had no municipal electricity, but had plenty of light at night from their simple solar lanterns. But more than this, I was able to have reliable lighting in the highlands of Nepal, using two sources of electricity that never would have been considered possible 10 years ago. The first was using a device I created called the Solar City's aluminum can tab torch that uses a joule thief circuit, a recent discovery in pumping electrons using transistors and electrons derived from waste aluminum foil and Coke can tabs. I figured out a way to create a flashlight that would run on the reaction of aluminum garbage and drops of wood ash lye gathered from local Sherpa fires. The second was a flashlight I bought that is powered by the Power Pot, a commercial application of the Peltier device, a thermocouple made of two metals that produces a small current when one side is hot and one is cold. In the past, you see, none of these energy sources would have been considered useful. But after super bright LEDs were invented in Japan in 1994, it suddenly became possible to get great light from very low wattage energy supplies, opening a whole new world of possibilities. Once I coupled the power pot to an inner tube of biogas produced in my home digester, for example, I was suddenly able to reliably cook and provide light and charge the mobile phone from waste heat and garbage. The basic idea for this lecture, then, is that there are certain disruptor technologies that act as game changers and that move society closer and closer to the point where our economic deadweight losses can be put back into service to create value. As Clayton Christensen writes in The Innovator's Dilemma, disruptive technology isn't necessarily a new technology. It's usually a recombination of existing technologies served up in a new way. Now, the problem with what society has considered waste and pollution for so long is that it generally simply was the right thing at the wrong concentration at the wrong place at the wrong time. I'd like to state that again. I believe that waste and pollution are mostly the right things at the wrong concentrations at the wrong place at the wrong time. Often the problem is simply the dispersed nature of material being wasted, whether it's low-grade heat or carbon dioxide released and dispersed in the atmosphere, or valuable heavy metals and organic chemicals released into the water, or scattered or dumped onto the land or in a landfill. The economics of gathering those materials or energy sources together and putting them back into useful form like Humpty Dumpty has previously made it less expensive to dispose of them. Now, certain technologies and processes, however, most of the recombination of other processes in a novel way, are changing those equations. One of those technologies is the humble garbage disposal, now called an organic feedstock preparation device, with the most popular brand name being the InSinkErator. This simple motor, invented in Racine, Wisconsin in 1927 and commercialized as the mechanical hog at a time when American urbanization was ending the age-old practice of homesteaders feeding food scraps to pigs, is now in about 50% of American households and makes it push-button easy to transform the problems associated with solid wet wastes into solutions, particularly when coupled with the process of anaerobic digestion. The parent company of InSinkErator, Emerson, is so confident that their technology is a game changer that about 8 years ago, when they invited me to their headquarters and factory in Racine, Wisconsin, to start working with them, they ran ads throughout Chicago's O'Hare Airport declaring, quote, grind virtually any kind of food waste into an unending source of electrical power for a city. It's never been done before. Consider it solved. So just as LEDs coupled with various low wattage energy source processes have suddenly opened up a whole new world of other technological opportunities that were considered impossible for centuries, the new appreciation for the ancient technique of anaerobic fermentation applied to urban food wastes is opening up incredible solution spaces and removing barriers. Another disruptive game changer is the modern megacity and urbanization itself, a fairly recent invention and phenomenon being looked at in new ways. As Edward Glaser points out in his bestseller, Triumph of the City, How Our Greatest Invention Makes Us Richer, Smarter, Greener, Healthier, and Happier, urbanization, seen through a systems thinking food, energy, water nexus lens, can be turned from a problem into a solution. By concentrating people and materials, most especially waste materials, in the built environment, cities make it possible to create what we call, quote, agglomeration economies that scale up and down appropriately. Let's explore, for example, how biodigestion impacts the use of what is known as plasma gasification, a promising technology for dealing with municipal solid wastes and industrial wastes, even toxic wastes that was previously considered too expensive, but which a societal reliance on biodigesters, made possible by the agglomeration economies of cities using their technology and infrastructure to grind and pipe all organic wastes, suddenly renders feasible. Plasma is the fourth state of matter and is best known in the form of lightning and the Frankenstein-like arcs of sizzling light given off by high-voltage Van der Graaf generators and electric arc welders. In plasma gasification, quote, a plasma torch powered by an electric arc is used to ionize gas and catalyze organic matter into syngas, with slag remaining as a byproduct. It is used commercially as a form of waste treatment and has been tested for the gasification of municipal solid waste, biomass, industrial waste, hazardous waste, and solid hydrocarbons such as coal, oil sands, pet coke, and oil shale. That from Wikipedia. One of the chief barriers to the use of plasma torch gasification, causing it to have negative net energy yields and frequent maintenance issues, has been that, quote, wet feedstock results in less syngas production and higher energy consumption, end quote, making, quote, investment and operational costs high relative to that of landfill and incineration, end quote. The game changer here is that wet feedstock is an ideal feedstock for biodigestion. And once a region decides to ensure all wet feedstock is diverted from source to anaerobic treatment, what is left over can suddenly be economically utilized with plasma gasification. Urban infrastructure already makes it easy to turn wet feedstock into a valuable commodity. The pipes and pumping and gravity flow mechanisms are already in place. As a city ordinance changing study called Clean Kitchen, Green Community, done by InSinkErator Corporation in Philadelphia showed, once homes and apartment buildings and institutional kitchens and restaurants and food processing facilities have installed food waste grinders, previously known as garbage disposals, into their sinks, there is no wet waste going into garbage bins and garbage trucks destined for landfill or discharge into our environment. Having food grinders installed as the default condition for organic material transports and aggregates the organic residuals almost effortlessly in a form that creates a net profit incentive for wastewater treatment plants or for dedicated biodigester companies, as we see with the Grind to Energy program in partnership with Quasar Energy and InSinkErator, to capture the value of wet feedstock. What is left over as municipal solid waste can then economically be used in incineration with much cleaner or more efficient results, or ideally with plasma gasification. A small shift in thinking, a move to nexus thinking, coupled with a simple technology, the food waste grinder, installed at the source to finally make source separation easy, is the game changer. Companies like Emerson Technologies, InSinkErator, and Quasar Energy are already aggressively pursuing the grind to energy solution, putting in the necessary front-end grinding and food conveyance infrastructure for institutions, while wastewater treatment plants, which already have anaerobic digesters in place and all the piping to receive the wet wastes, are all asking for reversals on previous municipal garbage disposal bans and asking consumers to please put food grinders in their homes and use them. The motive, as shown by the Grind to Energy advertisement, is the production of compressed natural gas, electricity, and heat, as well as abundant fertilizer. But a nexus thinker can see how the removal of wet waste from the trucked municipal solid waste stream immediately changes the prospects for plasma gasification and for several other technologies that have been lurking on the horizon for decades, but never quite seemed economical. For example, this simple change with the availability of abundant fertilizer in and near the city in liquid form suddenly shifts the economics for urban farming, particularly for soil-free vertical aeroponics and hydroponics, most appropriate for growing food inside and on the top of buildings. Previously, beyond the initial investment for hydroponic equipment, which isn't really all that complex or costly, the cost barrier for hydroponics has been for the expensive liquid nutrient solutions that replace soil. On the retail market, they can be as much as $25 a quart, up to $80 per gallon, and rare has been the urban farmer, besides those creating high-value crops like gourmet lettuce and microgreens and marijuana, who could afford to go soil-free. But biodigesters create liquid soil that recovers all the nutrients lost from the harvest and consumption of food in the first place. So we can anticipate that a shift to food grinding and digestion will create a surplus of local nutrient solutions that will drive costs down radically, permitting the vertical farming vision of Columbia professor Dixon Despommier to come to literal fruition. There are other advantages. An abundant supply of biogas, the only truly natural gas we have, in the built environment gives an incentive to change our generators and engines over to true fuel flexibility and ramp up production of clean liquid fuel derivatives from compressed biogas and liquefied natural gas to methanol and, what is perhaps the best possibility of all, dimethyl ether, or DME. We can start moving to what is ostensibly a natural gas society that can make use of all the fossil natural gas we have available and all their derivatives, but that also encourages every other fuel possibility, both fossil and non-fossil. This website on methanol tells us the advantages. The advantages are best illustrated by the enthusiastic spokesperson for Volvo and Oberon Fuels in their 2-minute video about dimethyl ether.
So Volvo's running heavy-duty trucks on DME. What's so great about DME? Works just like diesel. You can run it in a diesel engine, 18-wheelers, dump trucks, whatever, and it burns ultra clean. It's easy to store and handle. It's non-toxic. It won't hurt the soil, the water, the air. And here's what's blowing my mind. You can make it out of just about any kind of biomass. Say you're in farm country and you got a lot of manure. Pigs, chickens, cows. You can make DME out of that. And now Oberon Fuels has these mini plants. They're modular, on skids, so you don't have to take the stuff to the plant. You can take the plant to the stuff. Say you're in a mega city and you've got a lot of landfill gas. Throw it in a mini plant. You can make DME out of that. Say you're a large grocery chain and you've got a lot of food waste. Throw it in a mini plant. You can make DME out of that. Say you find a little natural gas in your neighborhood. Throw it in the mini plant. You can make DME out of that. Grass clippings, fat, grease, waste from breweries and bakeries. Yes, yes, yes. So it's clean, it's powerful, and it's sustainable. And we can make it right here at home out of just about anything. So what are we waiting for?
The methanol economy, which includes raw biogas and fossil fuel gas and all methane derivatives, from methanol to dimethyl ether, does not exclude coal and oil either. It simply cleans them up and creates a more diverse energy portfolio that can best make use of local resources. Even coal, for example, can be economically converted to methanol and DME when the market and infrastructure for flex fuel machinery and motors using these forms of hydrocarbons has been developed, as demonstrated in India and China. The key is having multiple feedstocks for useful products and knowing that we can rely on wastes, particularly urban wastes, to supply an everywhere available, local, cost-effective baseload supply that pays for itself because it solves problems and creates positive externalities. But we don't have to eliminate fossil reserves. We instead are free to price them and process them in a way that removes their negative externalities. I suggest that the disruptor here that may ultimately change the equation is a new appreciation for the nanoscale microbial world, whose performance is radically improved through grinding waste materials and a willingness of the energy industry to embrace the role their ecologies can play in production and transduction, and the creation of a clean and diversified portfolio of solutions. Certainly, those of us who work with the microbial world, whether in the biodigestion and composting arenas that I'm in, or the algae arena that Dr. Philippidis is in, appreciate how natural nanoscale processing organisms can supply much of the labor and catalytic reactions that made previous ways of obtaining clean renewable fuels problematic. Now the pathway from raw biogas itself, a product of cooperation with microbes, to methanol, and onward to tertiary products like DME is becoming recognized. Limitations are being overcome through selective breeding and genetic engineering, but also through the selection of synergistic ecologies of appropriate microbe consortia and better catalyst identification. There are other ripple effects that come from an application of grinding waste materials to improve surface area and digesting all organics. For example, once food wastes are no longer disposed of in single-use plastic bags and containers because they're being put into grinders and digesters directly, and thus soiled or contaminated plastics are removed from the waste stream. Recycling plastics, or using plastic-to-oil processes, becomes immeasurably easier. Already, the idea of shredding and grinding plastics to transform them into value is gaining traction at the DIY scale. A Danish company named Precious Plastics has published open-source plans for startup companies to build their own plastic shredders, extruders, injectors, and compressors, and proven the upcycling process. While the Japanese company, Blessed, has created affordable plastic-to-oil mini refineries, one, the educational desktop version I own in New York and used at Mercy College. Once again, the key to reducing labor costs and making it economical was the elimination of food waste contaminated single-use plastics, which was easy for us because we had built our own biodigesters to handle organic residuals. It's almost as if, simply by finding effective ways to incentivize the separation of organic and inorganic residuals by giving organic waste value, all the other pieces of the puzzle start falling into place. And when we don't want to or can't engage in plastics upcycling or plastic-to-oil transformations, microbes can be harnessed to downcycle ground-up plastics into nutrients again, into nutrient particles as economic conditions improve for the production of bioplastics, which a methane, methanol, dimethyl ether infrastructure makes possible. The following graphic shows how DME, for example, is a precursor for biodegradable bioplastic production. At the end of the day, what we see is that there are emergent properties that come out of the introduction of new technologies and recombinations of old ones in new ways. I studied with Dr. Michael Storper at UCLA, and Dr. Storper, according to Oxford Research Max Nathan in his 2017 article on urban incubators, innovation, and inequality, quote, highlights in his recent lecture, big cities are learning machines that help innovation and entrepreneurship to happen. He cautions, but the feedback mechanisms that drive urban economic growth also create persistent disparities between cities and within them, stating that, quote, much of what we're seeing today is ultimately a product of improving urban fundamentals plus technology, globalization, and policy shocks from the 1970s onwards. For urban economists, cities grow because the net benefits, agglomeration economies, amenities, outweigh the negatives, pollution, congestion, stress, high costs, end quote. He then asks, quote, what will future shocks, automation, climate change do to this calculus, end quote. I would contend that when we use nuanced food, energy, water nexus thinking embedded in a holistic systems approach at the core of our urban learning machine, and consider how the urban ecology and industrial ecology perspectives, that there can be no such thing as waste, challenges us to find new synergies, then there are also feedback mechanisms that can also create persistent and compounding advantages and accelerators. I hope I've highlighted just a few of the ripple effects that a recombination of grinding, digestion, and symbiosis with microbes can have on cleaning up our act with regards to fuels and fertilizer and currently wasted resources. As a final takeaway, if we look at how businesses are now applying Maloney's 16% rule to Everett Rogers' theory of the diffusion of innovation, we see that the way across the chasm separating the innovators and early adopters and the skeptics and laggards is to turn messaging about scarcity to one of social proof. As more and more living examples of the application of material waste grinding for improvements of surface area to volume ratios, coupled with anaerobic digestion and other microbial processes impacting the economics of plasma gasification and Fischer-Tropsch creation of clean liquid hydrocarbon fuels, are seen around the world, I think we will see a greatly accelerated shift of the curve, such that renewable sustainable technologies and the zero waste economy become the norm rather than the exception. And given that we now have the necessary agglomeration economies, thanks to urbanization, we should be echoing the question of Volvo and Oberon fuels. What are we waiting for?